Now we want to discuss actually calculating the Gibbs free energy for reactions. So just like we've seen previously for enthalpy and for entropy, we can calculate the change in Gibbs free energy for a reaction based off tabulated reference information that we call the formation Gibbs free energies. So these are very similar to the formation enthalpies that we saw, where it'd be the Gibbs free energy for forming it. And you would just, for an overall reaction, you would sum over products and then some minus sum over reactants. So it's the same idea using tabulated information. And again, corresponds to a particular temperature, and that little circle corresponds to it being at a pressure of 1 bar. So let's look at an example. What's the change in Gibbs free energy associated with the following reaction at 298 Kelvin? So I have barium oxide reacting with carbon dioxide to make barium carbonate.
All right, so we want the change in Gibbs free energy associated with the reaction. So we're looking at Gibbs free energy here. And so this is just another thermodynamic property that we can calculate for a reaction using our tabulated information. So we've looked at enthalpy previously, we've looked at entropy previously. Now we can do the same idea with Gibbs free energy. So we can take our reaction, we can say that, in general, delta G for the reaction is going to be the sum over products of delta G formation minus the sum over reactants of delta G formation. So it is the delta with the formation, just like the enthalpy was, because enthalpy is a part of Gibbs free energy. But it's just a matter of then finding, looking at the chemical equation. Everything has ones in this equation for the coefficient, so we can just use these values. So my product is barium carbonate, so it's going to be negative 1134.4 kilojoules per mole minus, and then we want to sum over all of my reactants. Barium oxide is negative 520.3 kilojoules per mole plus the carbon dioxide, negative 394.4 kilojoules per mole. And so when we take a look at this, this is actually a really common place. This kind of calculation is where we really tend to see arithmetic mistakes. This negative, we want to not forget, applies to both of these. So the negative goes there and the negative goes there out front. And so, you're there's lots of positive negative signs. So really do want to be mindful. One of strategies is just kind of combine all of these and then subtract it. This is going to be a negative number, so you're subtracting a negative number, functionally adding, but you just want to be mindful. That's a really easy place to kind of make mistakes that end up having nothing to do with chemistry, but cause some issues with getting the right answer. But we can combine those together. Delta G is equal to negative 219.7 kilojoules per mole, and we can figure out that's the delta G for the reaction. And really the main function of calculating delta G is just to look at the sign. And so we can see that we have negative sign. And so because it's negative, that means the reaction is spontaneous under these conditions. So at 1 bar, that circle means we're at 1 bar pressure, 298 K. If you react barium oxide and carbon dioxide, you're going to get barium carbonate.
So if you have your reference information, you can just look up your delta G's of formation for all your reactants products and figure out the value of delta G for your reaction. And what that really tells us is the reaction spontaneous based on just the sign of it. So if the only thing that you care about is this reaction spontaneous? If I mix barium oxide and carbon dioxide, I'm going to make barium carbonate. That would be a spontaneous reaction. So then the question becomes, well, why do we talk about enthalpy and entropy? And that's because if we want to know the question of why is this reaction spontaneous, just not more than just is it spontaneous? And that's where those delta H and delta S are going to come in, and we're going to be able to apply those to figure out why is this reaction spontaneous, and how could we maybe affect its spontaneousness by, say, changing temperature.
Participation 325, question 1. Does TiCl4 spontaneously boil at 25 degrees Celsius? I think, and then there's this table of thermodynamic properties that you will find very useful for completing this problem. Again, this is the first question on participation 325 due Friday, March 25th at 11:55 p.m. over on Blackboard. Link to the assignment is right below links to these videos. Again, does TiCl4 spontaneously boil at 25 degrees Celsius? And there's the table of thermodynamic properties that you're going to want to use to do this problem. You're going to need to use to do this problem. There you go. First participation question in our second video. Just getting started. Got a handful more videos to go. See you there.